Hello, hello. This is a very, very special video lecture. So, I'm really glad that you're here with us today. Why is it so special? Because it is, of course, lecture 10, lecture 10, right? Which comes after lecture 9, but it is also lecture 11. Yes, see how it is. See what I'm doing there with that 11th thing there? Not actual finger, but yes, I am combining in this video lectures 10 and 11. It's not going to be twice as long, but I have to combine the two. Why? It's actually an intellectual reason than a physical reason. Okay, this is why. Because what I'm about to tell you should, under normal circumstances, if this were a class that was specific, like say for a physics major or for a mechanical engineering student or something like that, this is the kind of class that would take 2 full lectures to talk about. But this class is not that, right? This is physics 1. And you have a lot to get to. There's a lot of material, a lot of fun, awesome physics to cover. And it's only a relatively short amount of time. So despite my impulse to tell you all the cool stuff that I would give you for these 2 lectures, 10 and 11, and make them long and beautiful and complicated, I'm going to try to condense them. They're not going to be as long as 2 whole lectures stuck together. But the goal is for you to get how important this rotational motion and circular motion and so forth is in physics. And then we'll move on to other things that are applicable to the kinds of things that you are learning. So in other words, think of these lectures 10 and 11 not as like double the material, but it's like 2 lectures worth of cool concepts being put together. And so the lecture study guide that you're doing, which you might be filling in already right now, right? The lecture guide might be a little longer than usual, but it's not going to be twice as long. It's not going to be all of that, because if we went through all of it, then we would be taking so much time that the focus of what I need to cover in this class will be diluted. Or, I'd have to sacrifice something else, which is super cool. So it's hard. It's hard. I mean, it's so hard because I like this stuff so much. I would share this all with you all day long. I could go into tremendous detail, but I can't. I must resist. I have to stick to the things that are most relevant to your course of study. That's okay, though. It's still cool. I mean, whatever I'm going to share with you is super, super cool. Okay, so what is it that I'm going to share with you? Well, remember in the previous lecture, we were talking about things like displacement, right? We come back to these sorts of things. Remember the idea of what displacement is, what velocity is, displacement at a certain time, the acceleration, the amount of time you're accelerating, the velocity change, things like that. And then we got to the equations like v equals v0 plus at, and then d at a time t, the displacement, remember, is the d0, displacement at time 0, plus the velocity at time 0 times the time. That's at this time t plus 1/2 at squared, where a is the acceleration, which is the change in velocity. Remember that? That was like the key aspect. And then if we improved, well, it didn't improve, complexified that aspect of one-dimensional motion, we thought about two-dimensional motion, right? What happens if you're like shooting something diagonally or pushing it off of a ledge or something, right? You're sending an object off the side, then it kind of has this two-dimensional motion, one which has, in this case, right, gravity coming down on it, and then the velocity, gravity does not come down on it. So you have 2 different equations that show the x and the y, and then you have to use this angle theta to sort of determine what component of the x-axis, what component of the y-axis and the motion is involved, right? So remember that the acceleration of gravity being 9.8 meters per second at Earth's surface, right? If we went to somewhere else, then we'd have different gravitational accelerations. And so that acceleration A might be different. It's just amazing stuff to start with, right? So now what we're going to talk about is a little bit the same, but kind of spinning. Because you see, if you're talking about motion in one direction, linear motion, like either in the x direction or the y direction or the z direction or something like that, right? That's Newton's laws originally. Newton, right? Momentum, motion, straight line, the first law, second law, third law, action equal opposite reaction, what force is, what energy, well, conservation of momentum is what momentum is, right? It's all really cool. But what if you're doing it around in a circle? And we've already had this conversation, well, we started this conversation, shall we say, earlier in the semester, right? We were talking about torques and balance points. Remember, we're talking about the center of mass and how you have to balance things. Things are going up and down, maybe using cans of tuna, I don't know, maybe using other stuff. And so you wind up with these ideas that you have to have a point. If you're marking your motion around a point instead of away from a point, but like how often do you go around it? Then you wind up with a whole nother set of cool things to think about. But in the end, this concept of displacement, right, is basically reproduced, but with really neat, interesting other consequences that happen. All right, and fun, cool physics stuff that's really relevant to the kinds of things that emotion within bodies, for example, or our systems or things like that, right? We talked about that a little bit. And we had my friend the brick, right? Remember, it's nerfed, so I'm not worried about it. Well, we have this brick here and it's going around. And when you are watching me spin this thing, right, you see that my hand is here, right? And I'm actually adding something like a twisting effect in order to keep it going around and around and around by moving my hand back and forth, right? And that's called torque. I've been adding some torque to it. And then as this thing spins, there's the momentum that the nerfed brick has, right? That, you know, actually clearly is a mass times a velocity, but in this case is a mass times velocity going around a point at a distance, right? At a radius from here to there. So that aspect we talked about before, and that was this, right? The concept of torque, angular acceleration, angular momentum, and then this thing, moments of inertia and angular velocity. Yeah, that stuff. We're going to revisit that because it's so cool, but there's so much of it that we can't, almost breaks my heart, that we can't cover it in these lectures 10 and 11. So we're just going to stick to the points that are relevant and valuable to your course of study, you know, as a biology person or a health professional person, something like that along those lines, life sciences. Okay, so be ready for that. And we're going to see all this stuff again. We're going to present it in the context of all that other cool thing that we've been talking about up to this point in the previous lectures, talking about things like displacement, right, which we had said over here. All right, so let's review. We can basically draw, well, almost parallels, right? Let's use parallels because that's very helpful. Okay, so we have these three laws of motion, right? Newton's laws. The first law, which is expressed by sort of, you know, the conservation of momentum. The definition of momentum is mass times velocity, right? And then you have a conservation. And then you have the force law, which is the second law, the definition of what force is, right? Force is a change in momentum. And then this third law, the law of reaction, right? The equal, every action is an equal and opposite reaction. This is sort of like the conservation of momentum, but for a system, right? If you have more than one object, say one object is pushing against another object, now you don't just have an object, you have a system of objects interacting, right? And that's Newton's third law. And it's basically the conservation of momentum with objects interacting with one another. You have a whole system in how they conserve momentum. That is super, super interesting and cool, right? So that, there's a whole another chapter on that in the textbook, which alas, we cannot cover. That would be rolled into this chapter, well, this lecture 10 plus 11 too. But we just have to just sort of know it exists and go by and just say, see ya some other time, we'll have another conversation about it. Now, if we try to match this up, okay, with P equals mv, the equation that matches the P equals mv equation is the angular momentum equation, right? And here's the angular momentum. I'll use the same format of this envelope, but I'll do it a little bit further down. So like the one equation, L equals R cross P, like that. Okay, so L, as you know from the previous lectures, angular momentum, right? Angular momentum is the radius of the rotation, right? In that case, the brick's case, the length of the string to the center of mass of the brick times the momentum of the brick. Now this times, as I mentioned in the previous lecture, is a cross product in angular terms. If you can do it, you don't have to do that if you are using trigonometry. You can also use, sines and cosines and things like that, which we're not going to do in this class because, again, just a little bit beyond the scope of what we're trying to talk about in this class, which is too bad, but that's okay. Second, and I put a second one, the torque, right? The force, remember, force is mass times acceleration. Well, torque, right, is this, but instead of momentum, it's force. Like the first law, remember, P equals mv, right? It has momentum in it. And then the force is the change in the momentum. So torque is the change in angular momentum. So it's R cross P, F, excuse me, instead of R cross F instead of R cross P, like that, right? And then the third law of this motion, right? Newton's third law of motion, which is translated into, the force from 1 to 2 equals the force from 2 to 1, equal and opposite, so minus. You can do that with torque too. So if there's two things that are interacting with each other, that for every torque, every action with a torque 1, 2, there is an equal and opposite torque 2, 1, like that, right? So this and this are very similar in their conversations, right? So in this case, this hasn't been annotated like I annotated over here, but we can do that. We can say what R is, we can say what tau is, and things like that. So I can put that down in a moment. Why don't I do that just to be sure? Okay, let's be sure. What is R? L, P, F, right? L equals angular momentum. Now, so these equations you can use for any kind of rotating system that you want, right? L equals angular momentum, and then R equals radius of rotation, right? The radius of revolution, the radius of the rotational motion, okay? So where are you going around? What is the fixed point? What is the axis about which you're spinning? And then we have tau, right? Lowercase t in Greek. That's the torque. That's the change in angular momentum, which we've done before, right? And then P and F are what we had known before, momentum, linear momentum in this case, not angular, and force, like that. Make sense? Okay, so far so good. Well, rotation turns out to be really important, right? Think, the wheel spins round and round and round, right? Everything turns. The turning is very, very important. I have here, I got a frisbee thing, right? Whee, that spins, right? That helps. I have this dreidel, which is a top, right? If I spin that on here, can you see? Whoa, it spins, right? There's cool stuff there. I have this rolling pin thing here. And look, I can spin this rolling pin. I can throw it like that. Whoa! That's okay. You can spin it this way, or you can spin it this way, right? Or you can spin it this way. Spinning is cool. Football, yeah, spin, right? The spinning this way makes a difference in how it moves, how it turns. So you can split it this way, right? Which is doesn't quite go through the air as nice as it goes into rectangular. Or anyway, I got lots of fun stuff. We can spin all these things all day long. We'd like to know more about them. Well, guess what? Long ago, after Newton, but not too long after Newton, people were thinking, you know what? Just in the same way that mass, right, is the property of an object, right? Mass is the property of an object. Its mass is a thing, okay? Maybe there is something that could take the place of mass in a spinning system. In other words, notice how mass directly affects or is a fundamental piece of information about the motion of an object, right? Its momentum or its force. Is there something else that can talk about rotation, like the mass, but like equivalent to the mass, but instead of mass specifically, it has to do with the rotation of an object? And so people worked on this and tried to understand. So if you have an object, right? I've got, all right, I've got this object, right? Okay, this object here, this nerfed brick, and I'm spinning it, right? This has an angular momentum, and it'll have a momentum. And then when you multiply it with me and with the thing, then you get this r cross p in the angular momentum, right? So that's a cool thing. But as you know, as we spin it, it's really waiting any time to go in a straight direction, right? And the reason it's not going straight off somewhere is because there's always a force held by the string held to the center of rotation where I am here. So somehow this thing, this brick, and this distance, right, has something that you can always count on to use, that if you can multiply it with something, some kind of velocity, then you would get some kind of momentum, in this case, angular momentum. And if you multiplied it with some kind of acceleration, then you would get torque. Can you do that? Well, first, let's figure out what that kind of acceleration is. What is the kind of acceleration that would most make sense in trying to understand angular momentum? It's not how fast the object is moving, right? But it's how fast it's spinning. And how fast it's spinning doesn't really matter about how far away the object is, but the actual spin of the object is what I care about, like the rate of spin, okay? So what I want is a velocity. Remember that, when we talked about the motion in a straight line, right? We have velocity, the velocity, right? The vector quantity, how fast you're moving relative to a location in a certain direction. Can we have something? We should have some sort of vector quantity that's like velocity, but it's going around and around in a circle instead. And there is exactly such a thing. And I'm about to write that down right now. And so that is where we're headed. We want now to have this thing called omega, which is a lowercase omega, it looks like a W, okay, but it's actually the last letter of the Greek alphabet, and it's lowercase, it actually looks like a little round W. Omega is angular velocity. So the velocity that you're going around in. Remember that velocity in a straight line is measured in the distance over a period of time, right? It's like, for example, meters per second. But instead, with angular velocity, you want to know how much angle you're going over a period of time, right? So the units of angular velocity is how much angle you travel in any given second, right? Now, usually you could use something like degrees per second because there's 360 degrees in a circle. But turns out that for physics, it's really useful to talk about radians. Remember radians? Those of you who are well-versed in trigonometry, right? Radians per second is a very useful way of measuring your angular velocity. So that's why we're going to stick with it. Remember that 2 pi radians is how much angle there is in a whole circle, right? So 360 degrees is also how much angle there is in the whole circle. So 2 pi radians is 360 degrees. That means that pi radians is 180 degrees, right? Pi over 2 radians is 90 degrees, and so on and so on. So all those pi and things like that, and the way that they go is very useful. So we count angular velocity in radians per second. And later on, as time goes on, especially if you do more physics and stuff, the radians concept is extremely useful. Those of you who have taken some trigonometry and then moving forward in some of the advanced mathematics that have to do with angles and rotation and so forth, you'll know why radians is very useful, because it turns out that number pi, right, the ratio between the circumference of a circle and the diameter of a circle, 3.14159265535, etc. That number is extremely fundamental to just about all kinds of math that we do in this world. It's kind of cool that that's the case. So angular velocity is measured in radians per second, right? Where 2 pi radians happens to be 360 degrees. Well, if you have an angular velocity, what's the change in angular velocity? Oh, it's angular acceleration, of course, right? So we write that down. So we say let's call that, since we're using Greek letters, let's just use a Greek letter that's sort of like A, alpha, okay? So alpha is angular acceleration. And that'll be in units of radians per second squared, just like meters per second squared is the unit for linear acceleration. Now, angular acceleration is radians per second, right? So if you're spinning up a car engine, for example, it starts slow, but you got to get it up to a few thousand RPM or something. How fast does it take? If you go from a certain number of radians per second at 0, and then at some few seconds later, you're going at some large number, then you divide and get the number of radians per second, radians per second squared, and you have that. So what is the thing that you multiply with these things to get your angular momentum and angular acceleration or torque? Well, excuse me, let me rephrase. What do you multiply with angular velocity in order to get angular momentum? Or what do you multiply with angular acceleration to get torque? Okay, that's another thing that you use. And so the answer, as it turns out, is this thing which we call capital I, right? You're going to see lots of capital I's useful in a lot of different contexts, different physics classes and so forth. It's even electric current, actually, for those of you who will be taking the equivalent class Physics 2 next semester. But this I, in this case, is called the moment of inertia. Like, you know how momentum and moment and how the first law of motion that Newton had was awesome. Moment of inertia is often called the law of inertia. Well, the moment of inertia, all right, and sometimes because people don't like to use the word moment, they like to use a different word, like a rotational inertia or something like that, just to try to be a little clearer. So sometimes you'll see that word, rotational inertia. So might as well write that down here, just so there's no confusion. If you ever see the words rotational inertia of an object, then you'll know what it means. It means the moment of inertia, or this capital I thing, okay? And that's always the case. So the moment of inertia, or the rotational of inertia of an object at a distance r, if you're going to try to figure out what that number is, it actually is for a point source, like a mass object of mass m, okay, going around a central point at a distance r, the rotational inertia of that point is mr squared, okay? But if you're rotating an object like this brick, it has length and width and height, the rotational inertia will vary. Just in the same way that like a massive object or a less massive object or more massive object has different masses, objects with different shapes have different rotational inertia values. Isn't that funny? I guess it's not that funny. It's pretty obvious, right? Some shapes are a lot easier to spin than others. I mean, if I can spin this thing, right? I can spin this thing around quite easily just by doing, whoa, that, right? I can spin it, whoa, like that. You know, it's really hard to do classroom demonstrations on the internet. That's okay. But spinning it this way is a little bit harder, right? It takes a little bit more effort to spin it that way. And you can spin it this way much easier. Similarly, if I'm trying to spin this dreidel, this top, right? If I spin it the way that it's designed, it spins rather easily. But if I try to spin it, let's say this way, right? It doesn't spin nearly so easily. If I spin this sucker, I spun this sucker earlier, right? One way it works pretty well. This way is really easy to spin. This way, it's a little bit harder to spin, right? It doesn't balance all that well. And the football, yes, go back, pass, yes, it's beautiful, yay. Spinning this way, as opposed to spinning that way, two different phenomena. So the shape of an object determines its moment of inertia or rotational inertia. And then where you're spinning it from matters too. That goes back to that center of mass thing that we were talking about earlier in the semester. Remember, like if you lean forward and you try to pick something up with your arms and your shoulders and and your back all stretched out, you're going to put a lot more force on the back muscles that are close to your spine than the actual force that you would have to feel if you held the whatever creature or object or person or whatever was closer to your body lifting up like this, right? Because of the distance is different, right? And therefore you have a different moment of force, we call it, or torque that you would experience, right? So in this case, it's the same thing. So where you are spinning it from matters. So your shape is important, but also where your axis of rotation is with respect to the shape. So the moment of inertia of this object, if I have it in the middle, right, I'm trying to spin it like this, is different from the moment of inertia if I try to spin it from here, right? You can imagine that. Or like this, if I spin it this way. Or if I try to spin it, I could even spin this object around my point here, like if I went round and around and around like this, right? That is a moment of inertia too. It's just a different one. So that's what makes rotational motion more complicated to figure out. Not harder, just more complicated than your typical moment or motion in a straight line. But once you get it, the math is pretty similar. You just have to figure out when to apply it properly in what location. So here, right, we have moment of inertia, angular momentum, and angular velocity. And we can now write Newton's first law, P equals mv, and second law, F equals ma, right? Using this, instead of using momentum and mass and velocity and force and acceleration, instead we'll use L, angular momentum, we'll use angular velocity, angular acceleration, and the moment of inertia will take the place of mass. So now I'm going to write at the bottom of this envelope those two laws that are will be remarkably the same as these two, but with a slightly different twist, something that is more parallel, matches more exactly what we were trying to do with Newton's first and second laws. So the first law of rotational motion, I'm going to write instead L equals I times omega, like this, right? And omega is a vector quantity because we have to know which direction you're going in. Are you going clockwise and in radians per second, or are you going counterclockwise in radians per second? So that's kind of important. So L equals I is a scalar like mass. It doesn't have a direction, but it matters where you count it from, depending on where you're spinning. So L equals I omega. And then in the similar way, we can do too, torque, right? Tau equals I alpha, like that. Right? Alpha is the angular acceleration. Once again, are you changing your angular velocity in the clockwise direction or the counterclockwise direction? That kind of thing. So L equals I omega and tau equals I alpha are analogs to P equals mv and F equals ma. And then when you want to write it without using the moment of inertia, you wind up writing it this way, R cross P and R cross F, which is the same thing, just packaged a little bit differently. Make sense? So this is the basis of the physics, the mathematical conceptual ideas of all this cool rotational motion. And now we're going to go to the textbook and we're going to run through all the analog information, right? The analogous, the analogies that we can make from one to the other with the rotational motion, with all these different L's and I's and omegas and things like that, right? And R's and F's and P's and so forth, with the linear displacement that we were talking about before. So why don't I go back and tell you all the rest of this great stuff, which most of which I'm afraid I'm going to have to skip. We're just going to have to go through it and kind of know it a little bit. The key point here for the rest of this lecture 10 and 11 video will be based on this chapter 10 here, 0.1 and 10.2 and 10.3. So we're going to get back to that in a moment. But let me just tell them to you first, and then we'll go back and you'll show all the other cool stuff that we see. All right, so here is the mathematical analogous action between linear motion and rotational motion. Okay, it's the introduction of rotational motion and angular momentum. A tornado, of course, is a classic example of an extremely vigorous rotational motion. And what often happens is people don't see this so much. You do see the cone, right? People know that tornadoes are cones. But what happens is that the rotation out here, the angular momentum, is very large, but the rotational radius is very large, right? The R cross P in R is very large. And then when it comes down the funnel cloud down to this point here, the r is very small. So the r cross p, if it stays the same, the conservation of angular momentum, right? Then as the r reduces, the p, or the momentum, increases, which means that the speeds go very, very high. So down here, sometimes, excuse me, sometimes wind speeds for tornadoes can reach 300 miles an hour or 500 kilometers per hour, right? And even like 100 or so miles per hour, 150, 160 kilometers per hour is enough to like rip apart a building. So you don't want that, but imagine even more strength than that. And that's how tornadoes work. It's also how hurricanes work, but in a different way. We'll talk more about that at some future time when we talk about heat and pressure. Oh, see, told you, we have so much that we have to talk about. Wish we could do, I really do wish we could spend like 2 long, beautiful, complex lectures on this, but we're just gonna stay focused. We're gonna keep moving. 10.1, 10.2, and 10.3 is what we're gonna finish up with today. Okay. Oh, that's Nancy Kerrigan. I don't know. Is it? It looks kind of like Nancy Kerrigan. It's probably just some other skater. Nancy Kerrigan is a famous skater from the 1990s. She was very good. She won a couple of medals in the Olympics and things like that. But see, here is what omega is, right? It's delta theta over delta t, or the change in the angular position, right? Theta, which is something that we've seen before. And then delta t, which is the amount of time. And then if you want to relate angular velocity to linear velocity, it has to do with the radius of rotation, just as we talked about. Omega equals v over r, right? If you're going around in a circle, that's how that works. But then the acceleration, right? Angular acceleration, alpha, which we just talked about, is delta omega over delta t. So here are some mathematical examples that you can run through and understand how that works. It's just straight math, but by understanding the physics of it, right, and how that all lines up, then you can do the math, and it's easy to understand compared with if you're just memorizing math equations for no apparent reason, right? And you can see how the angles and the vectors have to do with one another, and you can see how the acceleration changes and affects. So the alpha, angular acceleration, is the acceleration in the linear, like tangential direction, divided by r, okay? So you can use that information to figure things out as you wish. And here are the relationships that I was talking about earlier, right? Remember how x, which is, I used d in my backs of envelopes, but in the textbook, as you know, it uses x, which is fine, which is displacement, right? Velocity and acceleration. This is going in a linear direction, translational. But rotation, right? Theta is the angle, it's a displacement angle, and omega is the rotational velocity, or the angular velocity, and then angular acceleration. Angular velocity, angular acceleration, right? Whoops, I just jumped. And then we have displacement, right? Velocity, linear displacement, linear velocity, linear acceleration. And here are the mathematical relationships. Notice they've just got a little r over it. See, that's because there's a rotation involved. That's just exact translational rotational relationship. You can figure this out here later on if you wish, but that's the first part. And again, I'm zooming through this, but that doesn't mean it's not important. This part is probably the part that's most relevant, because what we're doing is just remember the V equals VO plus AT. That's an equation that we talked about earlier, right? Now, omega equals omega naught plus alpha t. Make sense? Yes, matches up pretty exactly. And now we're talking instead going around in a circle, right? These are the 3 equations that we talked about before, x or d, right? D0, some sort of original displacement, plus V0t plus 1/2 AT squared. By the same token, this omega, right, has an omega naught, or a theta naught, some sort of beginning theta, plus omega naught t plus 1/2 alpha t squared. Same kind of kinematics. Isn't that cool? And you can have average velocities and average accelerations and all that kind of determining. So there's a lot of good stuff you can do here. Fishing reel, some of you are fishermen. and Fisher people, you can figure out how fast your line rotates. How about slowing down? Okay, well, that's kind of interesting. How about trains and wheels and acceleration? How fast trains get up to speed, how slowly they get down to speed, how many radians, right? A thing will go around, but what's the difference between the number of radians? How many, just divide this by 2 pi and you know how many times you've gone around, you multiply by the circumference and you can figure out how many meters you've traveled, right? So these are the kinds of things they want you to do. This is a weird example, a fly in a microwave oven. You can look at that. It's kind of fun. The math makes sense. Anyway, so follow me so far, hopefully. And now we're getting to this. This is the definition of the rotational inertia. Remember, this book decides to use rotational inertia. I use moment of inertia, but they're the same thing. So I'll try to use the words rotational inertia fairly often, but you'll hear me say moment of inertia, and you'll see that in a lot of the online sources as well, which is totally fine. So this is how you calculate the moment of inertia. All right. So this, for a point, for an object at a distance r away, right, a point mass m. So here's the point mass m, and it's a force perpendicular to r exerted, amount of force F, then the moment of inertia, the number that makes torque equals something times alpha correct, is mr squared. So the rotational inertia or moment of inertia is mr squared if you have a mass m and you don't have a shape. But what happens is, of course, objects do have shapes. And as a result, you have to sum up all the mr squared for all the point masses that it's made up of. So you have a solid body, okay? We often call that in astronomy or in physics a rigid body. Rigid body rotation, meaning it's not liquid, meaning it doesn't flop, it doesn't have joints and so forth. And so when it spins, it makes a difference. Of course, we humans, we flop, we spin, we have joints and things like that. So the moment of inertia and the moment of force and the lever stuff, mechanical advantage, backs, shoulders, lifting, those things all matter very, very much in all this combination. But so, for example, if you have a hula hoop and you're spinning a hula hoop around the center, I don't know how you hold the hula hoop and just spin it. Just assume it's spinning. Like if you're in space, you can just spin a hula hoop around, right? Because all the points of a hula hoop are at a distance r from the center, more or less. Then assuming that the hula hoop is very thin, then the entire hoop is mr squared. Same thing as with an empty cylinder. But what about a sphere? What about a circle, right? What about a disc? What about a stick? What if you're spinning a stick? If you're spinning a stick in the middle, or if you're spinning a stick from the end, all those rotational inertias, the moments of inertias are different. And you can compute them if you are having fun with calculus. If you like to use calculus, or you can use some geometrical arguments sometimes without calculus, you can figure out the moments of inertia for any object. And it's kind of fun, all right? But there's no need to do that here, unfortunately. Or if there were a need, then I would tell you, but there's no need because, well, first of all, this class is based on things that are useful to you. The physics is really cool, and I want you to know it and understand it. For example, if we're talking about the spinning of the human body, right, either for entertainment purposes like ballet or figure skating or something, or if you're actually trying to figure out like the ability of different parts of the body to withstand stress, if you're a physical therapist or something like that, this rotational inertia is extremely important. But basically, this has all been calculated already by people, right? And if you take these pieces, it turns out you can add them all up. There's a really neat thing called the parallel axis theorem that allows you to add up different pieces of an object and then add them, stick them together and turn them into a single object and figure out its moment of inertia that way. All right. So this is really, really great stuff. And I am going to just tell you about it, and you're going to do a few practice problems on it and learn about it, and we're going to move on because there's so much other cool physics to learn. But just know it. Make sure that you understand it because it's that important and it's that neat that you can think about the spinning motion of objects in the same way that you can think of the linear motion of objects, just with some clever adjustments to what you're thinking of in your equations. Instead of mass, think of moment of inertia, right? Instead of velocity in a line, think of velocity in a circle, in an angular context, right? And then to wrap this up, I know there's so much here, and this is why this is 2 lectures worth. This is a part which, if we were in a full-fledged physics class, I would go to town with you. We would enjoy this and talk about this in such detail. You're just going to have to go with it super fast with me here, okay? And just so you know it, read it, understand it, and move on. All right, but know it and read it and understand it, though. You're going to do some problems, but you're not going to do nearly as many as we would if you were in like a physics class for physics majors or something like that. But if you're interested, there's a lot of stuff available, and I'd be happy to share that with you. It's very, 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 very cool. So let's just go through the part of all of this rotational activity, okay? And this is chapter 6. So I want you to be aware that this video, which contains lectures 10 and 11 rolled into one, right, to one unit, basically has elements of chapter 10 and elements of chapter 6 in it. And let's go back and remind ourselves about chapter 6 and then move on. So some of this stuff is review. We just talked about it, right? The delta theta, and we saw this earlier in the semester as well. 2 radians equals 1 revolution, a measurement between angles, and the angular velocity here, right? And how you can figure out the rotation, how fast does the car tire spin. Oh, this is just great and beautiful stuff. I don't know if you guys are vinyl collectors. What is with this fly thing on the vinyl? You know, I didn't write the book, but why not? Flies are cool. Actually, you know, some of us have issues with flies, and obviously we don't like them buzzing around our food. But you know what? Flies are actually really cool. Turns out that flies are important pollinators. They are important scavengers. They help clean our environment, and they're really good food for a lot of birds and stuff like that. So they're a really important part of our ecosystem. Just, I agree, we don't really want them around us. If we preferably have them, you know, out there doing their thing and not like buzzing around my dinner, right? That kind of thing. But anyway, flies generally are very cool. And we often think of just house flies, but there are a lot of flies, different kinds of flies in the world, including certain flies that like live for just one night as an adult, right? They actually have evolved in such a way that they're called mayflies. There's a kind of fly called a mayfly, and there's several varieties of them that they live their lives underground for almost their entire lives, sometimes even underwater underground. And then when they emerge with wings, all they're doing is coming up for one night, and then they're reproducing. They are basically fertilizing eggs and stuff like that, and then they burrow down under the ground, and then they lay the eggs, and then they die. And so that period of time when they're all flying is super cool and super beautiful, but it's very short. Sorry, this is a minor diversion from physics, but you know what? Science is just cool. Anyway, never minding the fly stuff. All right, moving on. We got to get back to the rest of this physics. Otherwise, this lecture is going to get way too long. It's already long, but not too long yet. Okay, so centripetal acceleration. Remember, we're talking about that, right? When you're going around in a circle, what's happening is that you're pulling on the object, just like when I had my Nerf brick, right? Zipping around my squeezy brick, and it's going around in a circle. You see me in a little tiny screen. I'm sorry, I'm just in that, right? The string is pulling inward toward my hand, and so therefore it's providing a restoring force that keeps it not going any further away from me, right, tangentially, but you have to continuously exert that restoring force, otherwise the object will go flying away in a tangential straight line direction. All right, so centripetal force, a little bit more conversation about that restoring force, right? And then you have the mr omega squared. You see that omega showing back up again, and how things are going forward and outward. And you have this so-called frictional force supplying the centripetal force. There's this really neat thing called rolling without slipping, right? And that's the idea where you're spinning stuff, and now you have some friction that's providing a restoring force, but at the same time you have the motion of the object overall, right? Even though this rolling object is rolling without slipping, the bottom of the wheel, right, has a net velocity of 0 compared to the center of the wheel, and yet it can move stuff forward in a linear direction. This rolling without slipping stuff is really kind of fun. And if we want to go back to the whole friction aspect and the centripetal acceleration and so on, we have the sine, cosine, theta, we have the normal force, the centripetal force, the net force, the restoring force. This is fun, cool stuff. But I want you to know it, and that's enough, all right, for now. And then we have the Coriolis force. You've heard of this before. I want you to know this. This is really interesting stuff. There's not going to be a lot of calculation about it, but you should read this and understand how it works. The concept of the non-inertial frame of reference, that goes back to Albert Einstein and his theory of relativity. And this is really neat stuff. I really want you to read it, understand it, and see why we think or why we feel a force that pushes outward while a centripetal force, that is something pulling inward, is in effect at the same time. It's a lot to do with this thing called Newton's third law, right? Where for every action, there's an equal and opposite reaction. But you can see here in the hurricane, right, as things are spinning, you see that the effect of a non-inertial frame, that is the Earth spinning on its axis, creates a situation where you're moving. You think you're moving in a straight line, but actually you're moving in a straight line with respect to a spinning Earth. And therefore, if you're not on the Earth, like if you're orbiting in a satellite or you're looking from a distant distance, you actually see the rotation happening, not in your point of view, but in the frame of the motion. That is super cool. And then, oh, as if that weren't enough, if you take an astronomy class, you will hear about Newton's universal law of gravitation in the extreme. In this class, alas, we're just going to know that it happens because it turns out that in the universe, the most useful restoring force, the most useful force, the thing that turns up most often in keeping things spinning and going around a center of rotation is gravity, right? Gravity is this equation, gmm over r squared here, right? The force of gravity is pulling inward, and this one doesn't have a negative sign, but very often astronomers use this negative sign. This is the magnitude of the force, and the m times the m, that's the little mass or a big mass or different masses, divided by r squared. Take an astronomy course, please, if you have the time. You can learn about how cool gravity is and how it is used effectively as a restoring force in the rotation of things. In our world right now, right, you've already done this a little bit. We talk about the gravitational acceleration of the surface of the Earth, and that comes out to 9.8 meters per second squared. And you're going to use that all the time. But look, you can figure out that the expression of the acceleration of gravity, right, due to gravity at Earth's surface, except it's not Earth, it's the moon, right? And what is the acceleration that we're talking about using the distance of the Earth to the moon, which is this many meters, and the mass of the Earth, which is that many meters. So actually the acceleration that the Earth has on the moon is tiny. The restoring force, the restoring acceleration is less than 3/1000th of a meter per second squared. But because the mass is so large, then the actual total force is gigantic. I mean, that's amazing, right? And then if you want to get really, really fun, you actually have wiggles, all right? The Earth's path moves. They create these things like Lissajous figures and precession and nutation and tides. Oh my gosh, tides. There is so much to talk about. What happens when a star gets swallowed by a black hole, right? Black holes do not suck you in like a vacuum cleaner. Rather, they are a gravitational source, and how you move. There's so much good stuff here. I would so love to go into greater detail with you, but alas, I cannot. And then Kepler's laws. Once again, please read this and please understand it. But we're not going to go into too much detail. I want you to know it, though. I want you to just be aware of how cool it is, because when it talks about motion in a circle or motion around a point, if you want to know how our planet, Earth, goes around the sun, or how moon goes around the earth, or how all the other planets go around the sun, how the solar system, how different objects move, how our sun goes around the center of the Milky Way galaxy. All those kinds of great cosmic awesome things that can be described by physics. Astronomers use that physics to do that. So you have Kepler's 3 laws of orbital motion, which is not the same thing as Newton's 3 laws of linear motion, but they are also fundamental. They are super cool. And I'm just going to zip right through because what can I say? It almost breaks my heart to have to not go through all those things in detail. But please read through them, fill them out in the study guide, get some understanding of how cool it is, and remember the aspects of rotational motion, right? How we have angular momentum and torque and reaction, right? The linear and the rotational laws work in parallel. And then if you use this concept of a moment of inertia, you can even write them just like F equals ma and P equals mv, right? This is super, super nice. Oh my gosh. And then from that, you can do all kinds of calculations. And then you have the displacement, right? Just as we had in the linear displacement, d sub t equals d0 plus v0t plus 1/2 at squared. This is the last thing I'm going to write down now. I have to do this because for rotational, right, it's so similar. So for rotational, and I know that this is almost like messing up this piece of paper, but it's not. It's just improving what I'm writing. For rotational motion, right? For rotational motion, I'm going to write it underneath here. Theta, right? The displacement in angle, theta sub t equals theta 0, right? Theta, that is the displacement at time 0, plus omega naught t, like that, right? Omega naught t plus 1/2 alpha t squared. Look how similar that is. Look how beautiful that is. It's amazing that, at least to me, it's totally amazing that if you think about how scientists have for centuries tried to figure out how things move and why they move. And now we're talking about translating that motion, not just in the straight direction, but round and around and around in a circle, or even an ellipse or some other cool shape. You wind up being able to connect these very same concepts in a parallel structure. Less to memorize, right? As long as you understand the concept, you realize that this is not just memorization. This isn't just facts that you have to regurgitate on something. No, it's the concept and the ideas that govern all of the way that we can think about motion. And only in this case, we're talking about going around and around and around in a circle. And then remember all this stuff. Yeah, about using the area under the curve between the velocity and time to figure out displacement. You can do that for angular displacement too, but instead of using v, use omega here, right? Instead of using a, use alpha here. These fundamental ideas are the same, just thinking about them going around in a circle instead of going in a straight line. Okay, I do have to stop here, but I gotta tell you, this is so cool. This stuff is so amazing. And I am very sorry that I can't go into greater and more beautiful detail over a longer period of time, but this is enough. This is a good sense. This is enough for you to start understanding and calculating some simple things and some straightforward things, but really knowing how things move and how they get displaced, as well as how they get pushed or pulled or moved around in a circle. This is really the fundamentals of that motion. And I'm glad that we were able to share it today. So thank you so much. Again, go through the study guide. If you have any questions, ask me, ask your recitation instructor, ask your lab instructor. We got fun stuff to learn. Thank you so much for your time. Have a great day. We will talk again in the next lecture, right? Which is lecture 12. Yes, 12. Okay, thanks. See ya.